Example 145. Randy Stinchfield of the University of Minnesota studied the gambling activities of public school students in 1992 and 1998. His results are reported below. Form a 99% confidence interval estimate of the true difference between the proportion of public school students who gambled in 1992 and 1998. Does there seem to be a difference? Okay, so in this problem, it's clearly a confidence interval. It says form a 99% confidence interval to estimate the true difference between the proportion of public school students, right, who gambled in 92 and 98. So we're comparing 2 years. They give us the data here. It's summarized below. It might be a little dark on the screen because of the way it printed in black and white, but I'll be able to copy that down for us in a moment. But basically what they give us is the sample sizes for the 2 studies, the number of people who gambled out of the group, and then they divide the 2 to give us sample proportions, p-hats here. So we'll have that for the problem itself. And when you're doing a confidence interval, we still have the same 4 steps. We're going to first list the data. So let's go ahead and do that for this problem here. The data in this study is going to be first, and again, we'll use 1992 first because the problem gives it to us first, but even if it didn't, it doesn't really matter, right? We could do it either way. We're just going to use that as our convention this time around. The sample size is 21,484 for that group. And the number of people who gambled out of that group, the X value is 4,684. That leads to a sample proportion when you divide these 2 numbers of 0.218. All right, then for 1998, we have a similar set of numbers. The sample size here is 23,199. Then we have a number of people who gambled. That's not X bar, I'm sorry, I swiped it there. It's just habit of writing X bar, but it's just an X value, and that number of people who gambled there is 5,313. And then from there, the sample proportion for that group is 0.229 or 22.9%. Okay, so we have 92, we've got 98, we have the information we need from there. We need to fill in a couple of things they didn't give us. We're going to need for a confidence interval Q-hats, sample Q-hats for each of these. We didn't need these in hypothesis testing, but the formula was different for the test stat and the hypothesis testing than it is here for the margin of error for confidence interval. And that has something to do with the fact that the null hypothesis in hypothesis testing assumes the 2 proportions are equal, whereas in this one, we do not assume that. Okay, so I'm just doing 1 minus 0.218. That gives you the complement, which is Q hat. And of course, that's 0.782. And of course, you could do that in your head. I just want to show you how to do it on paper, right? So it'd be 1 minus 0.229, and it gives you the answer 0.771. So those are our Q hats that go with our corresponding P hats. So here in the confidence interval, we're just going to need one more thing then, of course, which is the confidence level, right? So the confidence level here is 0.99, and don't forget that leads to an alpha of 0.01. All right, now that we have that, we can move on to our second step of the process, which is our critical Z value. Remember, for confidence intervals in this course, it'll be Z alpha divided by 2 always, right? So if you have large sample sizes or you're doing something with proportions where you're approximating the distribution by the bell curve, you use a Z value. And with confidence intervals, it's always alpha divided by 2. So for us, that's going to be Z.005. So we're going to go to our table now. We're going to go to the 0.005 column in the t-table and go straight to the bottom where the Z-score is located. So let's go do that right now and see what we get. Okay, so I'm looking at the 0.005 column and then going straight to the bottom to find a corresponding Z-score. So let's move the table up so we can see that. And the corresponding Z-score here is 2.576. Okay, so we end up with 2.576 as our critical value. And now that we have the critical value, our next step is to calculate the margin of error. Now the margin of error formula is different here. So it's going to be Z alpha divided by 2, that critical value we just found, then times the following square root. This square root has got 2 fractions in it, and the fractions are basically p hat 1, q hat 1 over n1 plus p hat 2, q hat 2 over n2. So it's essentially these pairs of P's and Q's multiplied, divided by their sample sizes, and then added together to form the total margin of error formula. So it's a little bit of work to plug all this stuff in, but let's go ahead and do it. We're going to have 2.576, then times the square root of p hat q hat, so in our case that's 0.218 times 0.782. And divide that by the n, which is 21,484. Then we'll do it on the other side, same thing. We're going to have the p hat and q hat, so 0.229 times 0.771, close it up, and divide by the sample size, which is 23,199. All right, so that's all the numbers plugged into the formula. Let's see what that is approximately with our calculator. Okay, so we have our calculator ready, and we're going to do 2.576 times the square root of, and the square root is going to be, you don't need any special parentheses here. You can just type these fractions in as you see them. So 0.218 times 0.782 divided by 21,484 plus 0.229 times 0.771 divided by 23,199. Close that up, hit enter, and you end up with 0.01, so 0.0101566461. So it's quite a long number, right? We're just going to store that in the calculator for use later. Of course, you could also round it off to, say, 3 decimal places and use it that way as well. But that's our margin of error. And once you have your margin of error, you're going to take it and finish the problem up by adding and subtracting it to the difference of the sample proportions. So here's your formula overall then, the last part of it. It's going to be p hat for the first group minus p hat for the second group, right? Minus the error, and then p hat for the first group minus p hat for the second group plus the error. Now, we're just going to be consistent here with what we started out with, so we'll use 1992 as our first group and 98 as our second group. Okay, so plugging that stuff in, we'll end up with the 0.218 minus 0.229 minus the error, and I'm going to round this a little bit, so I'm going to do 0.102, let's say. And then same thing on the other side, we're going to have the 0.218 minus 0.229, but this time plus 0.0102. All right, just squeezing that in there barely. All right, now finally, when we get that all filled in our calculator, let's see what it ends up giving us. So we'll have first 0.218 minus 0.229, right? Minus the error that we just found. And I put that in parentheses. I have no idea why, just habit of putting things in parentheses, I guess. But minus 0.021 is the first answer. And then we'll do that one more time, but this time we'll do add for the error. So we're going to add that error in, which I stored in as x. And this time my calculator gives me scientific notation. Be careful of that. You see that's an E there at the end of the calculator. So that means I'm going to have 0 point, and there'll be exactly 3 zeros before I get to digits. And the digits will be 8, 4, 3. Okay, so ultimately that's my interval then. So I'm going to finally finish this problem up by giving the wording here. We're going to say we are, because we use an alpha of 1% and a confidence level of 90%, 99%, we are 99% confident that the true difference, and that difference that we're referring to is going to be P for 1992, or rho for 1992, minus rho for 1998, right? So, in other words, the population proportion of gamblers for 92 minus the gamblers for 1998. So we're 99% confident that that true difference is between, and the number, again, we came up with is minus 0.021, and this was negative, by the way. I didn't put my negative sign in there. If you look back at our calculator, it was negative. So minus 0.000843. Okay. So this number is so small, this is almost 0, right? I mean, it's practically 0. It's not 0, but it's so small, it's almost 0. And this is about 2.1%. But in the end, it's not 0, this number, and both of these interval limits are negative. And if they're both negative, it means that the second number was bigger, right? So the second proportion was statistically larger than the first. So there's, it's a close case, right? And maybe if the alpha had been, something like 5%, it wouldn't be as close to 0 as it is. This last one is pretty close to 0. Remember, if it was 0, we would say that the difference could possibly be 0. And if it's possibly 0, then it could mean that there's not a significant difference. But because they're both negative, we're going to say technically there is a difference. And that difference means, in this case, since they're both negative, that 1998 has a larger proportion of gamblers than 1992. Remember that these rows here stand for the proportion of gamblers. So in 1998, there seems to be a higher amount of gamblers than there was in 1992. Okay, so that's the conclusion. And in the end, the confidence interval is just like a hypothesis test, right? In the end, somebody were to come along and make a claim and say, hey, I believe that the level of gambling is now higher in 1998 than it is or was in 1992, you could use this as evidence for that. You can say, well, yeah, the confidence interval seems to show that it is higher, even if just barely higher.